Hey everyone, Mr. Voikin here, and this is Unit 1, Lesson 2, Applications of Prime Factors. And we're going to start by looking at the greatest common factor, GCF. Now, before we can find the greatest common factor, we have to understand what factors are, and to do that, we'll look at the number 72. So the factors of 72 are all the whole numbers that can divide evenly into 72. And that happens to be 1 times 72, 2 times 36, 3 times 24, 4 times 18, 6 times 12, and 8 times 9. So the factors of 72 are 1, 2, 3, 4, 6, 8, 9, 12, 18, 24, 36, and 72. So let's take a look at two other numbers. We'll look at 108, 108, and 120. So the factors of 108 are 1, 2, 3, 4, 6, 9, 12, 18, 27, 36, 54, and 108. And the factors of 120, there are a lot of them. 1, 2, 3, 4, 5, 6, 8, 10, 12, 15, 20, 24, 30, 40, 60, and 120. Now, it takes a long time to list all those out, and then we need to search through all these numbers to find the greatest common factor. Well, I can see that 2, 2, and 2 are common, 3, 3, 3 are common, 4, 4, 4 are common, 6, 6, 6 are common, but the greatest common factor is going to be 12, 12, and 12. Therefore, the greatest common factor of these three numbers is 12. Now, this takes a long time, but it gets the job done. So let's take a look at an easier method by using a form of prime factorization. So we will begin by listing those numbers, 72, 108, and 120. And what we're going to do is we're going to look for a prime number that can divide into all three of those equally. Because they're all even, we can recognize that 2 can divide in there. 72 divided by 2 is 36, 108 divided by 2 is 54, and 120 divided by 2 is 60. Again, they're all even, so we know that 2 will divide in there, leaving us with 18, 27, and 30. Now, 2 will no longer divide into all three of those, but I can see that 3 is a factor of all three of those. 3 will go into here, leaving 6. 3 will go into here, leaving 9. And 3 will go into here, leaving 10. At this point, I can see there is no common prime number that can divide into 6, 9, and 10, so we are finished. Therefore, we look at the three numbers that are on the left side here, and the greatest common factor of all three of those numbers is going to be the product of those, which is 2 times 2 times 3, which equals 12. Okay, let's look at the second concept in this lesson, and that is the LCM, or lowest common multiple. So we need to know what multiples are, and to do that we will use the number 10 to begin with. And the multiples of 10 are 10 times 1, which is 10, 10 times 2, which is 20, 10 times 3, which is 30, 10 times 4 is 40, 50, 60, and that would just continue on infinitely. We'll try one more, or two more in this case. We'll look at 12. The multiples of 12 are 12, 24, 36, 48, 60, 72, And again, that would continue on infinitely. And finally, we'll look at the number 14, which is going to be 14, 28, 42, 56, 70, 84, ... So what we're looking for are multiples in each three of these that are the same, and I've only listed out the first 6 multiples of 10, 12, and 14, and so far there are no multiples that are common. Now if we continued these lists quite a bit further, we would figure out that the lowest common multiple happens to equal 420. Now, this takes a lot of time, it does work, but there is a simpler method. So again, we're going to use a form of prime factorization. So we will begin by listing out those 3 numbers, 10, 12, and 14. And we're going to look for a prime number that can divide into all 3 of these equally, and that would be 2. 10 divided by 2 gives us 5, this leaves 6, and this leaves 7. Now with the greatest common factor, we would look at these 3 and say there is no longer anything common, so we would stop right there and we would say our greatest common factor happens to be 2. However, with the lowest common multiple, we're going to continue going down this list. So we're going to now look and see, is there still a prime number that can divide into all of these, or any one of these? So 2 can divide into 6, leaving us with 3. It can't divide into 5, so we'll just put the 5 right on the line down there, and it can't divide into 7, so we'll just bring that 7 down as well. Another prime number that can divide into at least one of these is going to be 3, which will divide into 3 one time. It won't divide into 5, and it won't divide into 7. I'll do this again. 5 will divide into 5, leaving us with 1. I'll bring that 1 down and bring the 7 down, and finally 7 divides into 7 one time, and I bring those 1s down. And once I have 3 1s on the bottom, basically our lowest common multiple is going to be the product of the numbers on our left hand side, which is going to be 2 times 2 times 3 times 5 times 7, which equals 420. I'm going to do this one more time, this time using some larger numbers. So we will look at finding the lowest common multiple of 100, 125, and 250. So looking at these 3 numbers, I can see that the number 5 will divide into all 3 of those, leaving us with 20, 25, and 50. Again, 5 will divide into all 3 of those, leaving us with 4, 5, and 10. And here I can see that 2 will divide into 2 of those. 4 divided by 2 leaves us with 2. 10 divided by 2 leaves us with 5, and I will bring that 5 back down. Do this again, and I can see that 2 will divide into 2, bring down 1, and I still have our 5s. 5 will divide into both of those 5s, leaving us with 1. I'll bring that 1 down. Again, we have our 3 1s on the bottom, leaving us with the product of 5 times 5 times 2 times 2 times 5, which is better written as 2 squared times 5 cubed, which is going to equal 4 times 125, which is going to equal 500, and therefore the lowest common multiple of 100, 125, and 250 is 500. Okay, well, on to our third concept, which is the perfect square. So what are the, say, first 10 perfect squares would be 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. Now, what makes these perfect squares? Well, if we look at the number 4, we can see that 2 times 2 equals 4. For 16, it's 4 times 4. For 36, it is 6 times 6. And for 64, it is 8 times 8. So recognize that we've got a pair of 8s, leaving us with the square root of 64 equaling 8. We got a pair of 6s, and therefore the square root of 36 is 6. A pair of 4s, meaning the square root of 16 is 4, and a pair of 2s, meaning that the square root of 4 would be 2. Now, that's easy for these recognizable numbers, but what about when we get into a larger number such as 2,304? Well, what I want to do is I want to use prime factorization and break this down into its product of its primes. So we're going to divide 2 into there, and we're going to get 1152. 2 again will give us 576. And again, 288. One more time for 144. Again, 72 and 36 and 18. And 2 will go into there, leaving us with 9. And finally, we're going to break this down into 3, 3, and we're left with 1. So we can see on the left-hand side, I've got a pair of 2s, a pair of 2s, a pair of 2s, a pair of 2s, and a pair of 3s. Therefore, if I want to determine if this is a perfect square, we have to ensure that every one of these numbers is able to pair up, which they do. So yes, it is a perfect square. But what is that perfect square? Well, from this first set that we have right here, I'm just going to grab one of those 2s. So essentially it's 2, and from the second set, 2, and from the third set, and from the fourth set, and finally from the last set. This breaks down into 2 raised to the power of 4 times 3. 2 to the power of 4 is 16 times 3, and 16 times 3 is 48. Therefore, it is a perfect square, and the square root of 2,304 is 48. And if you were to punch that into the calculator, you would see that that is correct. On to our final concept, and that is the perfect cube, which is very similar to the perfect square, except a perfect square is only 2 numbers multiplying together. The perfect cube are 3 identical numbers multiplying together. So the first 10 perfect cubes would be 1, 8, 27, 64, 125, 216, 343, 512, 729, and finally 1,000. Okay, now how do we know they're perfect cubes? Well, I know that 4 times 4 times 4 equals 64, and 8 times 8 times 8 equals 512. So because I've got a triple 8, I know that the cubed root of 512 is 8. And because I've got a triple of 4s, I know that the cubed root of 64 is 4. But again, what about larger numbers such as 1,728? Is that a perfect cube, and how do we determine that it is? And if it is, how do we determine the value? Well, again, we use prime factorization. So 2 goes into here, leaving us with 864. 2 goes into there, leaving us with 432, and 2 goes into there, leaving us with 216. At this point, you should recognize that we have 3 2s. There is a triple, so 2 is going to be part of our final calculation. If we continue on, we can see 2 goes into here, leaving us with 108, 2 to 54, And finally 2 down to 27, leaving us with another triplet right there. If we continue on, I should recognize that 3 can go into 27, leaving us with 9. 3 goes into there with 3. 3 goes into there, leaving us with 1. We're finished, and we have another perfect triple. So, is this a perfect cube? Well, yes, because we've tripled up all the numbers. Yes, it is a perfect cube. So what is the cubed root of 1728? Well, that equals 2 times 2 times 3, which is the same as 2 squared times 3, which is 4 times 3, which breaks down to 12. So the cubed root of 1728 is 12. If you were to verify that on the calculator, you would see that we are correct. So we know that 12 times 12 times 12 equals 12 cubed, which equals 1728. Well, that ends the lesson on those 4 concepts, and as we did in the previous video, now we're going to move on to some questions. So here are your 3 questions to do for this lesson. Use prime factorization to calculate the greatest common factor and the lowest common multiple of 60, 168, and 330. Question number 2 is to use prime factorization to calculate the square root of 11,664 and to determine if it actually is a perfect square. And again, question number 3 is the cubed root of 13,824 a perfect cube? And if so, what is the cubed root of that number? So stop the video here, complete the work, and then start the video up again, and you can compare your work to mine. Well, here are the answers. For part 1 of question 1, the greatest common factor of those 3 numbers is 6. In part 2 of question number 1, the lowest common multiple of those 3 numbers is 9,240. Calculating the square root of 11,664 using prime factorization proved that yes, it is a perfect square, and the square root of 11,664 is 108. And finally, in question number 3, is 13,824 a perfect cube? Yes, and the cubed root of 13,824 is 24. Well, I hope this was helpful, and remember that continual practice is the key to success. And after this lesson, we'll be moving into lesson 3.